Well, when my colleagues have finished discussing the previous very beautiful talk by Chris, I will remind you that black holes are very common. Well, astronomers use words in kind of funny ways. They will also say that I was young because I'm less than 1 billion years old. So when I say black holes are common, I'm thinking of not the sort of little black holes you're probably familiar with, which only weigh 5 or 10 or 15 times as much as our sun, but ones that weigh a reasonable amount. And the nearest one of those is at the center of our galaxy, only 25,000 light years away. Really close. I told you astronomers use language a little loosely sometimes. Well, 25,000 miles away, light years away, 25,000 light years away is a black hole. It weighs about 4 million times as much as our sun. Now, black holes are called black holes because they're black, in the sense that they don't actually emit any light, but they have very messy eating habits. So if you're a star that's wandering too close to a black hole, you get eaten. And you might think that would be the end of you, and there'll be a sort of noise, and you would be gone. But no. Fortunately, black holes are really very untidy eaters. So the star comes close, they rip it up, they spread it all over their jowls, and it becomes really quite easy to see, because one of the characteristic things about black holes is that things near them move about the speed of light. And the speed of light, even astronomers admit, is really quite fast. So you've got the remnants of a star swirling around the black hole, and it gets hot and it shines. So much so that if the black hole at the center of our galaxy happened to be eating stars at the moment, and I'm glad to report that it's not, you would see a point of light in the sky about 1,000 times brighter than the brightest star in the sky. In fact, you'd see it during the day. So, black holes have the great advantage of not being very black and of being quite easy to see. Now, one of the things that happens if you happen to be a star that's been gobbled up by a black hole is that you tend to shine in really quite interesting ways. You don't just look like a light bulb or a star or something like that. You shine more like a neon tube. In other words, you give light out a particular wavelength that astronomers, clever people that they are, can recognize. So, if I happen to be looking for nice large black holes, I've told you what to do. You look for incredibly bright things in the night sky that don't look like stars. So why do we get paid to do this? Clearly, some astronomers get paid to do this so they can have a nice time chasing dodos in Mauritius. But not all of us do that. In fact, we're clean out of dodos these days. So the problem is that when I say they're very bright, they are very bright, but they're also a very long way away. So if I were looking for very, very large, very, very bright black holes that were a very, very long way away, things don't get quite so easy, because they're extremely faint to being a long way away, rather than just 25,000 light years away. And as I may have mentioned, 25,000 light years is really close. You know, astronomers have this strange sense of proportion. 10 years is not really very long, Chris, when you come down to it. After all, 1 billion years is roughly a short time in astronomy. So, interesting things. Very bright. Why on earth do we want to study them? What good is a black hole? Well, I guess if they're that bright, you could use them to read by. You could use them to deal with your garbage. You could dump your radioactive waste into them. But most astronomers don't spend a lot of time worrying about radioactive waste or garbage. They worry about learning about the universe. So it would be really nice to find something bright at the far side of the universe, because we can look at it with big telescopes. Now, that's a good thing to do. You can write papers, you can become rich and famous, but you actually have to learn something rather than being rich and famous as an astronomer. So, what we would like to do is to find things that are far enough away that by staring at them, we can learn something about what's going on, say, 1 billion years ago, or 10 billion years ago. And as many of you probably now remember, the universe is 13.7 billion years old. Now, when I was a boy, was very recently by astronomical standards, we didn't know how old the universe was. It was maybe 10 billion years, maybe 20. We don't know very much about what was going on 13.7 billion years ago, because things that have been that are so far away are kind of hard to see. So one of the games that was played for a long time was looking for objects that were so far away that the light has been traveling for, say, 12 or 13 billion years. We could tell us about the Earth universe. Okay, so here's the game. I want to find some incredibly faint things that are incredibly far away and have really weird colors. How do I do that? Well, what you want to do is to find things that have weird colors and look like stars, and you want to study most of the sky, because these are rare. So we built a telescope. Well, I didn't build a telescope personally, but my friends built a telescope. And we spent a lot of time in the mountains of central New Mexico looking through this telescope. Well, actually, we didn't look through this telescope. Astronomers don't look through telescopes. Astronomers' cameras look through telescopes. And I don't mean little teeny tiny cameras like the ones on your cell phone, partly because cell phones hadn't been invented at that point, and partly because we like bigger telescopes. So we built a camera with, in those days, 140 megapixels, biggest camera in the world. It's now in the Smithsonian. It's in a box near the Smithsonian, I believe. They promised they would put it on display, but they didn't, to my understanding, but we'll negotiate that later. So, we're looking for things that are very hard, very faint, and people have tried this before, and the record was pretty impressive, but it had stood for a very long time. So astronomers don't like to use things like light years, because that's too easy for the public to understand. So instead of saying light years, we say parsecs, but unfortunately, the general public cracked that code a while ago as well. So these days, we refer to distances in units of redshift. Okay, I can tell you what that means. It basically tells you how much bigger the universe is now than when the light was emitted. And the record has stood at 4.89, I think, for about 15 years. And we wanted to break the record. I've given you scientific reasons why we wanted to break the record, and there really were quite good scientific reasons. But it's also kind of fun to have found the most distant known object in the universe. So we settled down to do this. Now, you'd have thought this was easy. You're looking for things with weird colors in the sky. The trouble is that if you're looking at things with weird colors that are far enough away, and you take a photograph to a green piece of glass, you don't see anything. So you try taking a photograph to a red piece of glass, and you don't see anything. And you've already tried a blue piece of glass, and that didn't work. So you buy a piece of glass that only lets through the infrared light. So you look through your piece of glass, only sees the infrared light, and you say, I've got one. Now, it's kind of faint. So now the game we're playing is we're building a telescope, we're studying, say, a quarter of the sky. That's quite a big area. And we're looking for things that we can't see through the blue, the red, the green, or like I put in the glass, but we can see in the infrared. Great. There's a problem. Well, the first thing you do, of course, is that you find lots of garbage, things you don't really want. So what do you do about that? You find a graduate student. So we found a graduate student, and that was very straightforward. And the graduate student came to Princeton from China, but the camera didn't work yet. So this graduate student sat around Princeton twiddling the graduate student's thumbs for a while and taking classes. But we got the camera working eventually, and we had a graduate student. And this was a great part of the day, because I would go to bed in the evening, and I would sleep soundly, dreaming of all sorts of interesting things. And in the morning I would come to work, and I would look at my mailbox, or in English, pigeonhole, but we'll call it mailbox if you would like. And there would be a piece of paper, and on it would be written 4.52 and a spectrum. And we would say, exciting, we haven't beaten the record yet. And then we started finding pieces of paper in my mailbox saying things like 4.95, 5.07, and now we held the record. We were finding the most distant black holes in the universe, very faint objects. And then we got up to around 5.4, and then we stopped breaking the record anymore. This was a problem. The problem was I had to do some work, because the graduate student came to complain, and the graduate student said, the stuff you're telling me about isn't there. What do you mean? I looked at the data on the telescope, no, I wrote some computer codes, and I found this really fascinating object. It was a really red object, next to a really blue object, next to a really green object, a real coincidence. But there are some fascinating things here, it's definitely there. And the graduate student, who's now a professor in Arizona, said, oh, no, there's nothing there. And this was due to what most astronomers, most sensible astronomers, in other words, people like me, would call garbage in the solar system or asteroids. Because asteroids have this bad habit of appearing in your picture and then slipping away sideways. Because you only see them once. When you're looking through your blue piece of glass, you don't see them. And when you're looking through your red piece of glass, they're not there yet. But when you happen to put your infrared piece of glass up, the asteroid's in the middle of the field. So you think you've got something interesting, but you haven't. So we fixed that problem and we moved on. And then the next problem was that the graduate student was complaining that these weren't real either. And now the problem is the particle physicists. You see, none of these my thoughts, you understand. It's all the thoughts of some other sorts of scientists. But the particle physicists have particles, that's why they're called particle physicists, I guess, that have a bad habit of coming in from the sky and hitting our detectors and pretending to be stars. I don't know what the union would say about it, we should really object. But in fact, though we call these things cosmic rays, they're not mostly cosmic rays, they're mostly coming from the radioactivity of the telescope. So we can blame the engineers for that, but not, of course, the astronomers. Except that it turns out when you're looking through green glass, you see more of these cosmic rays if you're looking through infrared glass, because of radioactivity in the pieces of glass, and I suppose we might take responsibility for that. So these cosmic rays only hit once upon a time, occasionally, and usually when we're looking through just one particular filter. So these things also masquerade as something you only see in the infrared, not in the red, not in the green, not in the blue. So those were a problem. We eventually dealt with those, but that required some code and some thinking. So that's where I came into this. But eventually, I came to work one day, and sitting in my mailbox, there was a spectrum labeled 6.38. And for a very long time, that was the record-holding object. It was at a distance of 12.7 billion light years, and was giving out light from just around the time that the universe was first being ionized by the first star. So for a while we held the record, and not only was it the record, we could do some wonderful science saying, this is how the universe reionized a billion years after the Big Bang.